Hello everyone. In this video I'm going to talk about stitching together the wave function when we get solutions in different regions and what we have to do in the boundaries between those regions in order to get an answer that makes sense. Because this is something we're going to do quite often when we try to find the solution to the Schrodinger equation. Quite often we're going to be dealing with potentials where it might be constant for a while and then a different constant and then another constant or something like that. In fact, what we're going to do after this is the finite square well, which is pretty much just like this, although the same on both sides. And in fact, this actually works really nicely as a general technique because even if our potential is some weird looking thing, we can kind of approximate it as a bunch of regions, like sort of like this, and then maybe like that, and then, I don't know, like that and that, you know. To some extent, this is, for some purposes, that might be a reasonable approximation, and so we can just treat it, the potential as constant in a bunch of different regions and sort of stitch together those solutions as needed. So in order to do that, we need to know how we can stitch those things together and what the conditions are that we can use for that. So that's what this video is about. So what do we want our wave function to look like? Well, let me again write out the time-independent part of the Schrodinger equation, because that's what we're basically solving here. What do we want to be true about this wave function? Our wave function is a function of position, and we want it to solve this differential equation. We also interpret this wave function as something related to probability. So there are certain things that we'd like to sort of expect about this behavior of this wave function for it to kind of make sense. So for example, we want to have a wave function that is continuous. We don't want to have, you know, it can do this, but we don't want to have something that does, you know, that. Because one reason we don't want to have something like that, where there's a sharp break, is that we want, you know, we interpret, if we square this and sort of integrate over a region, we interpret that as the probability of finding the particle in that region. So if we look at, for example, between here and here, we get some probability of finding a particle in that region. But if we also look just slightly to the right, between here and here, we get some slightly different probability, or we expect it to be slightly different. You know, if probability is going to make sense, like if we move that region just a tiny bit, the probability should change in a smooth way. And that's why we don't want these discontinuities, because if we have these discontinuities, then we have, say, some small probability of finding the particle in that region, but all of a sudden, if we shift our attention just a little bit to the right, we capture that huge thing to the right, and all of a sudden we have a larger probability of finding the particle. The probability jumps discontinuously, because the function is not continuous. And we don't really want that. We don't really think that's physically sensible. So we want, whatever our solution is, we want psi of x to be a continuous function of x. So I'll just write continuous. We also want this differential equation here that we're solving to be well behaved. I forgot a little square there. And it involves two derivatives. If we want the derivative of a function to exist, then the thing needs to be continuous. It's another reason for something to be continuous. If a function is not continuous, then really I drew it as a vertical line, but really there's nothing. There's no values in between there. It's discontinuous. All of a sudden it goes to some new value. That means that at this single point here, there is no defined derivative. You just don't have a defined derivative. Mathematically, you can put this into better, more precise language, but the point is that if you don't have a continuous function, then its derivative just really doesn't, there's no sensible way of talking about its derivative at that point. Since this differential equation, on the left side we have a second derivative, and on the right side is supposed to be just the energy, we would really like energy to be defined for any particular point on this wave function. Or another way of saying it is just that we want this differential equation to be sort of sensible across the whole range that we're looking at. So another condition that we'd like about our wave function is that since it's a second order equation, it's got two derivatives, then we really want the derivative d psi dx to also be continuous. With one gotcha. We will find, and we have actually already seen an example where the derivative of the wave function isn't continuous. We've seen this infinite square well where we had standing waves. And where is the potential where is the derivative not continuous? Well, it's not continuous at the edges because it's zero everywhere else. And so that means you have kind of a sharp kink. So the exception here is unless, or actually I should write it this way, as we want the first derivative to be continuous as long as v is finite. That's the little caveat that we have to put in there. Most other cases, though, will have that. But that for that infinite square well, it's infinite. So we actually, that's what lets us escape from that, because we have basically an infinity there that lets our whole differential equation kind of blows up anyway. But those are the things. There are a couple other conditions that we'd also like, just for sort of physicality reasons. We would like phi of x to go to 0. I'll just write arrow. I'll just put an arrow. We would like it to go to 0 or as x goes to infinity and as x goes to negative infinity. It might go to 0 earlier, but we certainly don't want it to stay finite or even blow up or go off into infinity as x gets very large. Because ultimately, we really want to have a wave function that's normalizable. Because again, we're interpreting it as a probability. We want to be able to integrate it. So we don't want this thing to blow up in some weird ways that make it impossible to integrate. And because if we can't integrate it, then we can't really interpret things sensibly as a probability. So these are the conditions that we want, we're typically going to want for our wave function. And so, for example, if we're doing a solution in two different regions where our potential is, say, like this, we have maybe just a constant v here, and then maybe we call this zero energy down here. Then whatever this wave function is, we said in our previous video that if the energy is, say, less than the v, you have an exponentially decaying solution. If it's greater than the potential, you have an oscillatory solution. So we want an oscillatory solution over here and a decaying solution over here. Mathematically, when we do that and figure out what is the actual equation for it, what we're going to want to do is we're going to just match up. We want to make sure the wave function is continuous at this boundary. So we just want to make sure that the function is actually equal. And we also want the first derivative to be continuous. So if I draw an exponentially decaying thing here, and I'm trying to match it up to some oscillating thing here, I need to make sure that the function is continuous and that its slope is continuous. And so I just need to have something like this if I'm going to draw it out. And mathematically, that's what we want to enforce when we find the equations that are describing the actual wave function itself. And the function going to 0 as x goes to negative infinity is the reason that we have this rising exponential as we go to the right, rather than the exponential that goes the other way. We don't want an exponential. I draw it in red because we don't want it. We don't want an exponential like that. We don't want any. We want 0 of that because that's just going to blow up as x goes to negative infinity. It's not something that we can integrate. All right. So now we should be set up for doing the finite square well potential, and so that's where we'll go next.